Welcome everyone to the 2CC webinar series. Today we have Dr. Adri van Duin from Penn State University. He's a distinguished professor in mechanical engineering. And today he's going to be talking about a well-known piece of software called ReactFF. And in this talk, he's going to be talking about its applications related to 2D materials. Dr. van Duin, please go ahead.
Thank you very much, Kevin, for the introduction. So yeah, let me introduce my co-conspirators. First, my group members, Ciamao Nadir, who's certainly on currently on a sort of a semi-sabbatical in Turkey, Margaret Kowalik, and Jamil Hossein. Jamil just graduated in fall. And then also I'll show some of our recent collaboration with Kate Pless, who's at the Franklin and Marshall College in Lancaster, primarily in sort of educational outreach areas. So the topic is here is the application of ReactFF. So I will start my presentation by a very, very brief introduction to this method. This is by no means a method presentation. I really want to focus more on its applications. And as you see, there's a fair amount of application to go through. So I will not give probably each of them the credit that they completely deserve. But this is more or less sort of a giving idea of the breadth of the simulations that are going on in my group at this moment in time, and where they hopefully connect with the experimental efforts within 2DCC. Many of these things are driven by external projects, and so I'll label them accordingly during my presentation. And towards the end, I'll actually show a little bit more method development when I talk about ReactFF. So this is a method that we extend ReactFF with a limited explicit electron concept, and that's now mature enough that I thought maybe that this audience might have an interest in that and maybe come up with interesting ideas for applying this particular method. So ReactFF is a molecular dynamics based, it's an empirical force field method that can stimulate chemical reactions. It has been around for roughly 20 years, and one of the attractive features is that over the years we managed to develop it for a very, very broad range of materials. What it allows you to do somewhat uniquely is simulations of relatively large scales going up to 1 million atoms or beyond, time scales up to 50 nanoseconds, if necessary longer than that, of chemical events at complex material interface. Here on the bottom right is an example of a typical React example within 2DCC. So this is roughly a 5,000 atoms molybdenum disulfide system which we heat up, leading to all sort of defect structures. And also in the end, indeed, we see a transition of some of the solid phase into a gas phase configuration. So this is something that you can run on 2 or 3 processors, so not huge computational resources. And in 1 or 2 days, you can get a trajectory like this together. So it's essentially a relatively fast, computationally cheap way to get these type of results. And so within 2DCC, we try to embed it within a theory framework. So we typically train ReactFF using quantum mechanics-based tools. So density functional theory is pretty much the main workhorse there. Then ReactFF provide that connection from DFT accessible time and length scales towards a time and length scale that we can get data like reaction kinetics, phase stability, and all that can feed into computational fluid dynamics or phase field methods, which in turn can have length scales that can directly communicate with experiments. So this is kind of how we try to link multi-scale theory essentially with experimental efforts in 2DCC. So one of we have now a number of 2D materials have been expressed in ReactFF. And here's just some sort of various publications that have come out over the last couple of years. And that has been increasing the external interest in these force field parameters. So through the Material Computation Center website, we essentially have a relatively steady flow of requests for these force fields. And one thing that we also now aiming to do indeed is, and we are already making move towards that, is integrating ReactFF parameters and their training sets into the list organization to essentially make this communication more straightforward with external users. Also, and I'll come back to that later, we have Penn State has a Penn State-wide license for the AMS software, AMS ADF software. They just changed the names from ADS to AMS. That provides a very user-friendly graphical user interface for using ReactFF. I'll get back to that later in my talk when I show how Kate Plus is using this interface to essentially involve undergraduate students into this type of atomistic scale simulations. But this is also indeed something that we want to connect to list. So we can indeed have these type of computational workflows and capture them and organize them in lists, so that the external users can have relatively easy access to the computational setup. All right, so within 2DCC, really our first contribution, this is a relatively old slide from about 2016, was the development of a molybdenum disulfide force field. And so we typically indeed train these force fields against density functional theory data. That was done by Yongxi Wang, who was until 2 years ago was a member of 2DCC. And so typical things that we put in these training sets are down below. One thing that's what we've typically focused in was things like vacancy energies, but also vacancy migration barriers. And so we have now expanded that, and that's been driven by Nadir in my group, expanded this molybdenum disulfide force field to tungsten disulfide, molybdenum diselenate, and tungsten diselenate. So we have essentially all this, that entire family of materials described. And so the next couple of slides will show some of the application domains that we're looking for. So one area, and that essentially was driven by an external user project by John Maurer and Joshua Maurer and co-workers. We combined this molybdenum disulfide force field with an existing Reactive F description for silica, in particular hydroxylated silica surfaces. And that was based on experimental observations where they found that if they use gallium treatment to turn a passivated silica into hydroxylated silica, they show significantly accelerated growth dynamics. And so we've been using Reactive F to essentially develop, first of all, we developed this joint silica molybdenum disulfide force field. And then with that in hand, we can essentially look at how the molybdenum grows on these silica surfaces and how indeed the hydroxyl groups can play a role in that. And so using DFT data from Tao Wang, we essentially managed to validate Reactive F. We indeed found that Reactive F can very well reproduce the effects of hydroxyl groups on these surface kinetics, and find out that the hydroxyl group play a key role in accepting the original molybdenum trioxide species. Just molybdenum trioxide with bare silica, it does react, but it's a relatively slow reaction kinetics. The hydroxyl group can essentially initiate these surface reactions by doing a proton transfer from the silica surface to molybdenum trioxide, and after that, the molybdenum trioxide goes to a low oxidation state, becoming much more amenable to reacting with the surface oxygen. So the protons play a kind of a key, almost sort of catalytic role in starting that surface nucleation. So this is something that we currently we have a manuscript, a relatively mature manuscript that we hope to push out in the next couple, in the next months or so. But this shows how indeed with these tools we can see how the surface protonation state can greatly affect surface growth kinetics. Another topic that we and many people in my group have been contributing to is essentially the concept of gallium intercalation for defect graphene. So that's in collaboration with John Redwing and Josh Robinson's group. And so we've been looking at various aspects of that. And I'll just show you some highlights of areas that we've been involved in there. One area is to see how does gallium actually and similar metals actually make it to the subsurface. That is a pretty complex process. So quite often what one might do experimentally is use plasmas or other type of tools to make defects in the surface. But what we found is that these defects are very dynamic, not surprisingly. So they're quite reactive. And if you, for example, were to use a trimethyl gallium as a source, you can indeed see that these species can essentially react with those defects and sometimes even heal those defects, which essentially might make it harder for the gallium to get through. So we can actually at the React level, we can look at these defect dynamics and see indeed what is the sort of the thermodynamic end state, or at least intermediate states for the defect, and how that indeed affects the gallium migration through these materials or the gallium accumulation on the surface. So here we see, for example, on the top left, how the gallium migration barriers as a function of the type of defect. So we go from 4 vacancies or a quad vacancy, a relatively stable vacancy concept, to a single vacancy. Now the single vacancy is experimentally not a terribly viable defect because it's very dynamic, but at least at the React level, we can relatively quickly capture these type of concepts and figuring out what are essentially the type of defects that might be the most amenable towards gallium transport. And then we can look at things like gallium accumulation. Does it accumulate on top of the surface? Does it go below the surface? And how does it density migrate through these materials? We can look at things like charge transfer. It can be very, very key to these type of events. And so more details are described in these simulations in our recent carbon manuscript that essentially shows indeed the dynamics of that gallium graphene interface as a function of defect structure. Now, this is only actually part of the picture, unfortunately. So here we start essentially with a bare graphene defect, which is to some extent, well, to a great extent, an approximation. The real structure is even a level more complex than that, because indeed the actual defects themselves will interact and quite often get functionalized, especially if you make these defects by means of an oxygen plasma, but you actually may not even have a sort of a bare graphene defect, but you may have hydroxyls, maybe even nitrogen groups on there. And so we've been looking at indeed how these oxygen functionalities or other functionalities interact with the gallium species. That is work that has been primarily done now at the DFT level, with the aim that we can eventually turn this DFT data, use these DFT data to develop a Reax description, and essentially allowing us to look in more detail about the dynamics of interactions of the gallium with these type of surface functionalizations. Another area, this is a collaboration with Daniel Reifsneider and the group. We have essentially, as you saw in the early movie, that's one thing that works quite well in the React level is the migration of grain boundaries. And that's actually there clearly the unique experimental capabilities at Penn State allow us to do an almost side-by-side comparison of surface microscopy and Reactive F simulations, where we can see how, for example, grain boundaries interact with each other, how they merge, and how individual defects might, for example, move around, join a grain boundary. We can look at temperature effects. Typically at a React level, we may have to ramp up the temperature a little bit above the experimental temperature, but we don't have to go to crazy high temperatures. I mean, even at 500 Kelvin and 400 Kelvin, we see a reasonably good dynamics of these grain boundaries. And so that gives us some confidence that we can indeed make that comparison experiment quite well. So this is essentially a manuscript that's currently under development, where we show these sort of side-by-side simulation experimental migration of grain boundaries. Switching topics now, this is work from Margaret Kowalik, where we essentially are collaborating with Sai Baku and Nassim Alem's group, looking at a relatively complex concept. We have essentially a bilayer graphene, and we have a sort of an misoriented bilayer graphene and oriented bilayer graphene. And the experimental observation that we were asked to explain was why the oriented bilayer graphene lead to a much, much higher nucleation of tungsten diselenate. As you see here in the misoriented, there's hardly any growth, and oriented, there's essentially a large amount of growth. And so we've been looking into that. And so you see these are pretty complex concepts. Yeah, we have here two layers, and clearly you see that the structure of these bilayers can take many shapes and forms. But the oriented, there's a relatively ordered A-B stacking, but especially in the misoriented, you see indeed that these patterns are going to get very, very complex pretty soon. And so we were thinking, well, what we were particularly looking for is how can the oriented versus the misoriented, how can they accommodate strain in the graphite? The idea here being that these things are typically supported on the metal surface, and that means that there's typically a sort of there's different thermal expansion between these, and as such there may be a different level of compression in the two layers. And so our approach here was to see how indeed the oriented and the misoriented, how they would accommodate these type of strain distributions. And so this is the type of simulation we try to do then. We have essentially a bilayer, and we essentially put strain on them. And that indeed gave very interesting results. If we look at the misoriented case, we see that the strain gets pretty much accommodated. Both of the graphene layers kind of bend. And we get you see there's not a lot of interesting things related to nucleation going on, because there's a very, very, very weak curvature going on here that we don't expect is going to change the chemistry very strongly. However, in the strained case, you see a very, very different response. In the strained case, in the oriented case. The oriented case, I guess the we see that this strain here expresses itself in a high curvature domain. So a very different response from the misoriented case. And so our hypothesis now, well, is indeed that this leads to high local curvature, and this local curvature can then interact with the gas phase chemistry. So the high curvature domain has a significant higher amount of dihedral strain, and essentially is significantly less conjugated, leading to potentially faster chemical reactions and indeed nucleation. And so this is kind of going into the boundaries of the Reactive F theory, because we don't actually describe the registry of these graphitic materials terribly well, but we can essentially, we do describe the A-B stacking reasonably well. So we are feeling, so there are some issues there in the theory. We would really like to be able to expand the React theory here to get this more correct. But we feel indeed that these type of curvatures is something that we would expect to see in the oriented case and much less so in the misoriented cases. So this is pretty much where that comes out to. So the oriented case gives us all this localized buckling, while the misoriented case really doesn't give us any sort of localized buckling. We get a much more even strain distribution. And indeed, we tried this out so somewhat naively, but we just took a tungsten atom and we just placed it on the oriented case where we have this high local buckling. And we put it on the misoriented, and then on the oriented case, we saw that the tungsten atom binds with almost 3 eV. So that's a pretty strong bond, and more than enough to essentially keep the tungsten there even at relatively high temperatures. Whilst in the misoriented case, there's almost no bonding, only minus 0.2 eV, which is under the experimental condition essentially pretty much something that is not going to lead to any growth event afterwards. And this also now Chian Mao in my group then did a similar type sort of study on how curvature and graphene affects. This is in this image we have this from the tungsten perspective, but we also can do this in this case from gallium, or we can do this with selenium as well. And we find in all cases indeed that this localized curvature has a very strong effect on the binding energy of these type of species. So we expect them to at least accumulate near these high curvature sites, but also the binding energy is strong enough that this may lead to maybe defect formation inside the graphene and then subsequent growth-related chemistry. So changing topics. So this is an external project from Mike Chandros at Sandia. So he's interested in the molybdenum disulfide we discussed, but he's interested more as a sort of a tribal chemistry concept. The idea is that they clearly molybdenum disulfides are known as to be very good lubricating materials. One of the disadvantages, however, is that over time they may get oxidized, so silver vacancy gets oxidized, and this oxidation essentially leads to an increase in friction. And so what they do experimentally is they add certain additives. In particular, they add things like titanium and gold. And there's evidence indeed that if you add these sort of additives, that the oxidation levels go down and essentially leading to superior friction performance. So Chian essentially developed a interface between our titanium. We already had a pretty good titanium dioxide react description. So Chian expanded that to silver. So we kept a couple of molecular species. We also were interested in clearly the titanium sulfur molybdenum. So we did these type of angle distortion studies, and then train Reactive F against these species. So these are pretty small molecules, so you can relatively quickly do the DFT calculations on those. And then we essentially did 4 types of simulation. We took a pristine molybdenum disulfide exposed to oxygen. Then we added a certain amount of defects. So we took about, we removed roughly 10 silver atoms. Then that's the second row over here. Then we essentially take the pristine plus oxygen plus titanium, And finally, we do the defective molybdenum disulfide plus oxygen plus titanium. And we did it at a range of temperatures going from 300 Kelvin to 2700 Kelvin. Not surprisingly, at 300 Kelvin, not a lot of things are happening, but the defected molybdenum disulfide case, so where we essentially have a couple of sulfur vacancies, at sort of moderate temperatures, in this case 1500 Kelvin, we already begin to see significant oxidation damage. And the oxidation damage then leads to very significant type of more structural damage when we go to higher temperature. And here really temperature is kind of used as a time accelerant. That's not completely clean, clearly, because time and temperature are not equivalent. But in this particular case, it allows us at least to give some glimpse at what is the long-term stability of these. So we see that a pristine case is clearly significantly less prone to oxidation. But even there, we see at 2700 Kelvin eventually that we begin to oxidize this. Now, if we add titanium, then we see indeed that titanium very strongly works as an oxygen grabber. So it really removes the oxygen to a far extent from the gas phase. And that indeed means that even at elevated temperatures, we only see a minor amount of damage. And even in the defective molybdenum disulfide, we essentially see how the titanium essentially protects the molybdenum disulfide from oxidation damage. We can express this in various ways and forms, and this is clearly a rich source of data. There's also the data science games you can play with these type of plots, but you can essentially see where the localized damage is and how the damage then propagates into more substantial structural damages. In this particular case, we use essentially the coordination number as a sort of a tool to gauge the damage, but there's clearly other ways to do that as well. So this is actually pretty fascinating from a sort of here are some snapshots on the right, what we actually see, and also how essentially the titanium organizes itself. So the titanium, not surprisingly, makes the titanium dioxide relatively quickly, and the titanium oxide clusters kind of merge relatively fast into a bigger titanium dioxide agglomerate that sometimes spreads itself over the environment. But we see indeed a very interesting interaction between the molybdenum disulfide and titanium dioxide, where the titanium dioxide kind of actively looks for the oxidation sites and gobbles them up and essentially protects, in that case, molybdenum disulfide there. So we're beginning to run the same thing with gold. In gold, we expect clearly gold is also known to protect the molybdenum disulfide from oxidation damage, but clearly the mechanism for gold doing that will probably be very, very different from titanium, given that clearly gold is far less prone to oxidation. But so this was actually the force field development stage. So this was relatively short. And so this demonstrates how we can relatively quickly use these force fields to look at complex material interfaces once we have them in place. Okay, so you saw this slide before. So I just want to sort of change topics now towards more educational aspects of this. One attractive feature of Reactive F is just that it is extremely responsive. So many of the Reactive F calculations, you can set them up, and in a couple of seconds or a couple of minutes, you can have at least a meaningful response. And that's clearly very different from a density functional theory calculation, where if you set with the system, almost always you have a couple of hours of simulation time or more until you get a responsive feature from that. And so this fast response combined with a user-friendly environment like AMS makes Reactive F of significant interest as a sort of an educational tool. And so in collaboration with Kate Plus, we have essentially been investigating that. Kate Plus is working at the Franklin and Marshall College. And so she's essentially been working to expose her students in chemistry to essentially the AMS Reactive F capability and see if that could help spark their interest in these type of material science topics. And so this actually works remarkably well. So she exposed this to 50 students, and essentially that resulted in essentially 10 students actively getting involved in these type of simulations. And also a significant subsection of that, 80%, essentially signed up for a second semester, clearly having, and so what really drives this is the fact that is indeed AMS software that provides a graphical user environment that is quite responsive. So you don't have to work for all sort of text files and all that to get going. And we, clearly also what helped there that within 2DCC, we already had 10 or 20 of these force fields pre-parameterized, so that they were readily available within the AMS framework. And so they could be used straight off the bat. So where we want to go with this, whoopsie, there we go. And so here are some of the students' responses. Indicating indeed that one of the key things about there is just the amount of interactiveness that this is. So you can actually do something that in a minute you get a meaningful response, and that's really very encouraging for the, especially the undergrad student level. And so that allows them to build up the complexity in the research. They get a very, very strong early feedback, and then later on selling a longer research project gets easier because they are simply more aware of the of these methods. So this is where we want to go in the end. So Kate Plas already had a collaboration going on the copper silver nanorods, and that's really where we want to go in the end with this, develop force field to that. But by now already her students can get experiences in these type of silver selenium exchanges using existing molybdenum disulfide selenate force fields. And so they set up, there's just some examples of the type of simulation that they can do in a couple of minutes, a couple of hours time or beyond. They can look, for example, at, you take a molybdenum disulfide slab, you add vacancies, and you look at how these vacancies might interact with each other. So you can clearly put them in clusters, you can put them separate with another, you can change the distances between the vacancies, and relatively quickly, and each of these simulation points is probably just a couple of half a minute or a minute time or thereabouts, you can essentially get a response. And so this essentially sets up the student for being able to do longer scale simulation, larger systems down the line. So the future plans is to see if we can expand this. So we have clearly a larger community already there. And indeed, some of the experiences we might be able to reinsert maybe in the Penn State undergraduate experience as well. And so now indeed also a couple of the students, Kate students have now signed up for longer research engagement in summers, where essentially can expose these for a couple of months of more intense research experience. One thing that we already started this month is we want to now indeed start developing the copper silver force field. So my group will essentially set up the basics of that, and also would like to make that force field development somewhat interactive with what Kate students are doing, so that it can get at least some sort of involvement in that process. Okay, for the last couple of minutes of my presentation, I want to show introduce some sort of new theory concept that we have developed. So what we talked so far was all about Reactive F force fields. We have recently expanded Reactive F to Reactive F, which essentially includes a limited explicit electronic degree of freedom into Reactive F, where we can look into detail about electron migration, and that means essentially that we can look at electron conduction concept, but also concept that electrocatalysis and these things, which are a bit hard to address with Reactive F. So Reactive F was first sort of developed in 2016, and then recently we have been expanding that towards graphene. So that was Jamil Hossain's work, and I just want to show some of that graphene work here because that might be of interest to this particular community. So what we do in Reactive F is essentially the following. We introduce a sort of electron particle. It is a classical particle, but what it does is it changes essentially the valency of its atom host. So normally in Reactive F, carbon has a valency of 4, so it can make 4 bonds. In Reactive F, if the carbon grabs an electron, then its valency goes down to 3. And indeed, the CH4 radical anion would typically then like to break a CH bond and go back to a CH3 anion, and so that the location of electron essentially changes the chemistry of its atom host. So that's in a sort of a brief nutshell is what Reactive F tries to do. And it also indeed breaks sort of gives us a communication channel between charge and bond orders, which is something that is missing in Reactive F. And one thing that really directly comes out of that is that things like electron affinities, which are Reactive F arguably not that great at, so everything in Reactive F has a positive electron affinity, means that every molecule pretty much likes to grab electrons. That is not true. I mean, CH4 and water, for example, have very significantly negative electron affinities because their radical anions are very, very unstable. While on the other hand, from like an OH radical has an enormously high electron affinity because the OH minus anion is a very stable anion. And so in Reactive F, we can describe these type of electron affinity trends much better. And so this concept was then used by DeMille. This is primarily with a sort of a battery simulation aim, that we can essentially do a simulation. Here on the top, we have a lithium cation. It gets exposed to a graphene with an excess electron. And we can see that during the simulation, an electron essentially transfers from the graphene to the lithium cation and essentially makes a neutral lithium after that. So this was trained against a relatively extensive training set of electron affinities for a wide range of species. Electrons orbiting around the nuclei. We also put in there in-plane and out-of-plane conduction of electrons, equations of state for graphite, and similar types of things. And then this is essentially was our validation simulation. This is a graphene anion, so I have a graphene sheet with one excess electron. Now, essentially every atom has an electron by itself, so there's no distinction between the electrons. We just have one of them labeled red so that you can actually see its motion. And we see indeed over time that the electron kind of spreads itself out pretty evenly over the graphene lattice. And if we do this in graphite, we see indeed that this migration only is in one plane. So it doesn't transfer in the C direction. It really restricts itself to the highly conductive AB direction. We can make it more complex. We can, for example, add a defect. And then we see that the electron tends to kind of concentrate itself quite strongly around the defect. And so this is indeed something that you could directly compare with a DFT calculation to see if you can get that localization of the electron well captured. And we can do relatively fancy things like, for example, add an sp3 linker, and then indeed find that the sp3 linker provides a reasonably good conduit for the electron. So over time, indeed, the electron can now spread itself out over two sheets rather than being isolated on a single sheet. So this is now something that we're clearly in the battery concept. This allows us to make a much better distinction between lithium cations and lithium metal. So we can indeed over time transfer electrons to lithium cations. Once the lithium cations become neutral lithiums, they can essentially turn locally into a lithium metal that can plate. And this is clearly something that also can be done reversibly. So this may be a concept that could be quite relevant for other 2D materials. We have now also developed this, for example, for various oxides and similar species. So we can certainly develop it for other types of 2D materials. And it may give us an entrance into describing electrical conductivity to some extent, especially when we look at things like complicated structures like grain boundaries and all that. And also maybe items like electrocatalysis, how the location of the electrons might affect the chemical reactions at these surfaces. So that brings me to the end of my presentation. So the bottom line, we have here a method that essentially can describe a wide range of elements. And the transferability is key here because we can relatively quickly take a set of developed force fields, merge them together, and then work on complex interfaces like you may have seen here, for example, in the molybdenum disulfide titania types of work. The key part is computational cost. So Reactive F is not as accurate as quantum mechanics. We try to get it as close to the quantum mechanics accuracy as you can, but it allows you to run much, much larger systems. And quite often in the type of comparison that you'd like to draw, the size of the system is very important because there's clearly many things that you cannot really evaluate at a small, let's say 100 atom system. You really need to go to larger systems to express vacancies, to express grain boundaries and the migration over time. Okay, that brings me to the end of my presentation. I'll be very happy to hear your questions.
Thank you, Dr. Van Duin. Anyone can unmute themselves and ask a question at any time. If you don't feel like asking it out loud, just chat it in the chat box to Kevin. I'll ask you a question, Adri.
Sure.
In a broad sense, what is your dream simulation in terms of impact? What is it that you can't do now that you really want to do?
Sure. I would really like to go and to, for example, really start from the start of a synthesis mixture and grow at least a sort of a nucleus large enough that you can say, yes, I now have a stable nucleus in place. I can maybe start figuring out how my growth conditions like temperature, pressure, and all that may affect initial defect structures and all that, and make that reproducible and also make that environmental dependent. So a little while ago, we did this, for example, for carbon nanotube synthesis, where we looked at things like the size, how the size of the nickel particles affected the type of carbon nanotube that you synthesize. So we would really like to start doing that within 2D materials and look, for example, how your support structure can drive your local growth kinetics. So those are the type of simulation that I really would like to move towards.
What's your biggest barrier in doing that?
Yeah, the biggest barrier is really, it is still the force field development stage, I think. I mean, you have to convince yourself that you describe binding energies and key transition states well enough. So you need to clearly populate that first at the DFT levels. And once you have it understood to some extent, the basic fundamentals at the DFT level, you need to express it into training set that you can, and so that is a relatively slow step. Once you get to that stage, setting up the molecular dynamics is typically, at least your initial molecular dynamics, is not that hard to do. Now, clearly, there's a lot of things that you have to learn from EMD. And also what happens quite often in your initial molecular dynamics, you may learn of chemical steps that you hadn't even considered in the force field development. So that sort of interaction between the chemistry that you observe and being able to question that well enough to say, okay, this is where probably the method is somewhat inaccurate. That communication can sometimes take a little while.
Anyone else? That should get the question started. Stunned silence, Adri. You must have really put them back in their seats today.
Apparently I did.
Apparently you did. And that's okay. So I'll stop the recording now, and then if people feel like asking questions, can you just stay on the line for a few minutes?
I can certainly do that, yes.
This is the last seminar in the spring series. Thank you so much for coming online. We'll now stop the recording.